A critical point is an interior point of the domain for which f prime of c is going to be 0 or is going to fail to exist. Now, that is interesting because before, in the previous video, we saw that when we had a maximum or a minimum, then immediately the slope of the tangent line was 0 at that maximum or that minimum. What's going to happen, however, is that the converse is not true. And f prime of c can be 0 or even fail to exist without any indication of having a maximum or a minimum. Now, take a look at the following example. Local extrema can occur at point C where f prime of c does not exist. In this first function, we have a local minimum at C. So for example, if you take an area around this point, clearly this point is going to be smaller than all the others in the function. But clearly f prime of c does not exist because the function is not continuous. Okay? So notice that there's no relationship here with the fact that there's a local minimum and f prime does not exist. On the other example, we have a peak. So clearly there's a local maximum in there, but it turns out that the derivative does not exist in there as well. Why? In this case, it's because, remember, when we're approaching by the limits, the limit by the right is not going to be the same as the limit by the left, the limit of the secant slope. Okay? So when we get to the tangent point, the limit is not going to exist. And f prime does not exist, but we still have a local maximum. So we can see that there is that situation in there. However, it is possible that f prime of c is equal 0 without having any local maximum or minimum to occur. This function that we have here is an example of that. Notice that the slope is flat. We have f prime of c is equal 0, but we don't have a local maximum or local minimum going on. It's also possible that f prime fails to exist, but we don't have any string going on. So this is this example over here where we have a tangent line that has infinite slope, and clearly we don't have a maximum or a minimum going on. Critical points are candidates for local stream points, but you should actually determine if they correspond to an actual maximum or an actual minimum, because that might not happen. So the first example is going to be the function f of x equals x squared log of x. Notice that we're not defining any given interval. We mentioned before that it's always good to know if we are in a closed or open interval. So since there is no indication of a closed interval, we're going to assume that we're in the open interval minus infinity to infinity, which immediately is going to fall down to 0 infinity because that's the domain of the log function. Okay? Now, let's take a look for f prime of x and see if we have points where the derivative is 0 as does not exist. So the derivative is 2x log of x plus x squared times 1 over x. So we simplify this a bit. It's 2x log of x plus x. Clearly, this is the region where this function does not exist. Is a big interval. This function does not exist in minus infinity 0 close. So we can't use all those for critical points. They're not going to be a maximum or a minimum cluster or anything like that. So we're only going to have the option of f prime of x being 0. So when that happens, that means that x times 2 log of x plus 1 is equal to 0. And that gives me two options, x equals 0 or 2 log of x plus 1 equals 0, which means that log of x is minus 1/2, which means that x is equals e to the minus 1/2, or 1 over the square root of e. Now, those are my two critical points. But notice that because 0 is not in the domain, so we're very quickly going to disregard that as my option for a critical point. So my only thing, my only candidate, real candidate, is 1 over the square root of e. It turns out that actually is going to be a local minimum for the function. If we take the graph of the function, we're going to have that 1 over the square root of e produces a y value of minus 1 over 2e. And that reflects in a local minimum for the function. Now, however, I don't have a clear way of defining when this function is going to have a maximum or a minimum. I just took a look to the graph and say, oh, okay, so this point that is a candidate actually is the minimum. But what about if I don't have the graph? Okay, so we want to explore in the future methods to account for that. So the first procedure for finding absolute streams is going to be given in closed intervals. So we're going to assume that the function is continuous and it's in a closed interval AB, so we can apply the stream value function theorem. And what we're going to do is we're going to locate the critical points that are candidates for maximum or minimums, and we're going to evaluate them together with the endpoints of the interval. Then after that, we're going to choose the largest and the smallest value from the values that we just got, and we're going to see who's the maximum and minimum values respectively. So now let's make an example of that with the following function. We have the function f of x equals x to the 4 minus 2x cubed on the interval minus 2 to 2. So that's f of x, x to the 4 minus 2x cubed, and minus 2 to 2. All right. So first thing, we take derivatives. F prime of x is 4x cubed minus 6x squared. Clearly, this is a polynomial. So that means that the domain is all the real numbers. F prime exists for all r. So we're not going to have those critical points that comes from where the derivative does not exist. So now the only alternative is where f prime is 0. And that implies that 4x cubed minus 6 squared should be 0, or that x squared times 4x minus 6 should be 0. And that gives me two options, x equals 0 or x equals 6 over 4, which is 3/2, which is around 0.5. Now, that's going to give me, again, now my critical points, 0, 1.5, and I have minus 2 and 2 as information as well. So now I need to find who are the biggest and the smallest in here. So I set up f of minus 2, f of 0, f of 1.5, and f of 2. Clearly, f of 0 is 0. And f of 2 is also going to be 0. Notice that this, if you factor x cubed in here, you get x minus 2. So that separates the two zeros of this. So this is 0, this is 0. If you do f of minus 2, notice that you get minus 8 in here, and with a minus 4 in here as well. So minus 8 minus 4 is going to be 32, which is a very large value. Now we're going to have 1.5 cubed and 1.5 minus 2. This is good to know because although I can calculate what that is, very quickly I'm going to know that this is a value that is smaller than 0. This is a negative number. So immediately this is going to be my minimum, and this is going to be my maximum, just by comparing the values in the function here. Okay. Now let's take a look at the graph just to make sure that what I said is true. And so if I take a grapher tool, notice that that translates into that. And of course, as I was mentioning, the maximum is occurring at -2. We don't really have a local stream at 0 or at 2, and the absolute minimum is going to occur at 1.5, which is going to give me a value of -27/16, so a negative value in there. Okay, so this is the way that we use for approaching finding absolute minimum and maximums on closed intervals. Let's go for another example where we actually going to have the situation of the critical point where the function does not exist. So for that, let's take g of x equals x to the 2/3 times 2 minus x on -1 to 2. Now, as always, I need to do derivative. So the derivative of this is going to be 2/3 x to the -1/3 times 2 minus x plus x to the 2/3, and I get a -1 from the derivative here. Notice that this negative value is going to give me a denominator essentially. And for that, and to simplify that, I need to multiply by x to the 1/3 up and down. That way, I'm going to be able to fix having a negative on the powers. Now, notice that x to the 1/3 plus x times x to the -1/3 is going to become x to the 0, and x to the 0 is 1. So that becomes 2/3 on the top. So this is 2/3 x 1, 2 minus x. And over here, x to the 1/3 with x to the 2/3 is going to become x to the 3/3. So that's x. And this is all divided by x to the 1/3. Now, if I simplify this, this becomes 4/3. And this is 2/3 minus 3/3 is -5/3x. And so that's my simplification of the derivative. Now, at this point, I'm ready to find the critical points. So I have two options. G prime of x is equal to 0, which means that 4/3 minus 5/3 x is equal to 0, which means that 4 is equals 5x, or x is equals 4/5, or I have that x to the 1/3, or well, actually the case where g prime does not exist, which means that x to the 1/3 is 0, which implies x equals 0. Okay, so there are my critical points. Now, with the critical points in the extreme values, we check what is the maximum and what is the minimum. So let's find out what is g of -1, g of 0, g of 4/5, and g of 2. Clearly, g of 0 is going to become 0 because of this, and similarly, g of 2. Now, g of -1, this becomes a 1, and this becomes a 3. So we have 3 here. So far, it's looking like this is the maximum, and let's see if we have a positive or negative value. We plug 4/5 in this function over here, and then we're going to get that this is around 1.0 something. And so comparing, you can see that obviously this is not going to be a minimum because we have these zeros and these zeros. Since we have that the maximum is in one of the extremes, then the minimum is likely to be in the interior. And so 0 becomes the candidate for becoming that local minimum. Of course, this 4/5 is going to be a local maximum inside, but it's not the absolute maximum. The absolute maximum still is going to be this 3. And so let's take a look at the graph to see what it says. So now we're considering the graph of g of x equals x to the 2/3 times 2 minus x between -1 and 2. So you can see these lines are the end of that domain. You can see that the maximum over here is going to occur, of course, at -1, like we call it. The minimum is going to occur at 0. And the shapes make sense. And finally, the value of 4/5 is going to be a local maximum over here. Okay. Then we go back to being 0 on the other string. So with that, we can classify that this is absolute max. This is our absolute min, and this is a local max. And our classification is complete.